This is lab 12, associated with lecture 12, and this lab is on variable selection. And so we're going to do kind of a real quick recap on how to actually use some of these variable selection things in R to choose some variables and choose the best model. And we're going to be working first with a real simple example, and then we're going to work with a more realistic example. And so the first thing we want to do is we want to load two packages. The first one is our favorite mass package, and that's for some data. And the second package we're going to install, which you or load, which you might need to install, is called the leaps package, and that will have the variable selection functions in the package there for you. So we'll load those up, and we're going to work today with the empty cars data set. So we've seen this data set before. It has data on a bunch of cars and miles per gallon, cylinder, displacement, horsepower. All these variables relate to the engines of the cars. And what we're interested in today, and we've looked at before, is predicting the miles per gallon from these other covariates. And so we've done a little bit of that. You can get some help on this by, of course, looking at question mark empty cars, which tells us what these variables are. So miles per gallon, number of cylinders, displacement, horsepower, weight, etc. And the function we're going to use is called reg subsets, which is from the sleeps package, and it's going to be used for selecting variables. And you use it a lot like you use the LM function to build a regression model, but it's going to do a bunch of it's going to try out a bunch of different models for us, and we can use it to choose the kind of best model. And so let's just look at how to compute, how to use it before we read all this. So again, we're going to work with this data set. It has 11 variables and has 32 cars in it. One of those variables is MPG, so we have 10 other covariates we want to predict with. And with the way that we use this reg subsets is just like LM. So we're going to predict MPG from our other covariates. We're going to pass it the data, empty cars, and then we need to pass it two other parameters here, two other arguments. One, which is method, which is how it's going to determine how to go through and search through the model. So this is using a forward selection. So this is a greedy optimization approach to choose the best model. And then nvmax is the number of variables maximum to try. In this case, we only have 10 variables, so we can try up to 10. 10 variables is not that large, so we can actually search through all the models, not in not too bad of a fashion. If you have 1,000 variables, you wouldn't want to search through all of those, even potentially with a forward selection. So you do have to choose a maximum number to set to look through. So we can run this, and notably, it takes no time at all to run. And in fact, the algorithms of the past kind of 50, 70 years have been developed for fitting these things have become incredibly efficient. And so fitting, 10 models here, or a bunch of models here, is really, really efficient for linear regression because these things have been incredibly optimized, incredibly studied. Now we can look at a summary from SS mods, which is my subset mods. It gives me information. It gives me this table in particular, which tells me, for instance, for one variable model, what's the best variable, which has a star. So that's WT, which is weight. If I want to go up to a 2-variable model, it will include number of cylinders and weight. Right? Again, we're predicting MPG, so it makes sense that weight, number of cylinders is going to be related, and those are going to be the best predictors here. I have 3-variable models, cylinders, horsepower, and weight are the 3 best. And so the way that our forward selection here builds this is it finds the first best one, then it adds on, which is weight, then it adds on the second best one, which is cylinder. It takes weight and cylinder, adds on the third best one, horsepower, and then adds on a fourth best one, which is AM, whatever that is, and go forward, right, until you get to the 10-variable model where everything's included. Now we could do this in another way. We could do backward selection. So if we do a backward selection, it's going to start with the best 10, and it's going to remove one at a time until we get down to a 1-variable model. Notice here our 2-variable model here using a backward selection is different than it was using forward selection, right? This is a greedy approach. They're not necessarily going to agree. There are different ways of searching through the space of possible models. So in this case, our 2-variable model has weight and q-sec, which is the quarter mile second. And again, really performance, it makes sense. So that this is kind of the backward selection. You could also use an exhaustive search. And for 10 variables, you can do an exhaustive search. You could try all of them. And so here is what the kind of table we would get if we try everything and try out, and so this is an exhaustive search which draws all 2 to the 10 different models, which is about 1,000 different models. Notice that took almost no time to fit because of how optimized this is. Of course, it's a small data set, and we only have 10 variables, so you can do an exhaustive search. You couldn't do that if you had 1,000 variables or a huge data set. So other things we can look at, the summary of my models here has a couple different things. It has some metrics, say R squared, RSS, adjusted R squared, MALO-CP, BIC. It also has this which matrix, and which is just going to tell us in a matrix of true and falses for the model 1 includes the intercept, includes weight, nothing else. Model 2 includes the intercept, includes weight, and what's the second one? Includes cylinders, right? So it's a way of kind of getting that information out in another way. We could also look at, say, R squared, which is a metric. I can plot that. But notice that, as we know, for training data, this is a training R squared is just going to monotonically increase because adding more variables will never decrease the R squared. Okay? I could plot RSS to get a similar picture, monotonically decreasing, because adding more variables will never increase RSS. I could instead look at adjusted R squared, and adjusted R squared penalizes things for having, it's kind of in between a test metric and a training metric. It's penalizing my metric if I have too many variables. And so as you see, we actually get a peak, and then adjusted R squared starts to decrease. Basically what these metrics are doing is there is some model under which this is an estimate of training or the testing error. That's a whole other topic for a different course, but they're basically trying to get some kind of estimate of the test error using the training data. And so it looks about 5 variables here. I can ask which, and indeed it says the maximum. If I use which.max, it says the maximum adjusted R squared is achieved at 5. And so I could build my 5-variable model. I could build this model according. I could say, okay, I'm going to choose the model with the 5 variables. If we go back up to my table, all the way back up here, 5 variables has displacement, horsepower, weight, q-sec, AM. Okay. So I can grab those off of, I can grab the 5th row of my which matrix, grab those variables. And I'm just going to do a little bit of some cute text processing here to get my best variables. I'm going to grab the column names, which are in this 5th row. My best variables are displacement, horsepower, weight, q-sec, and AM. And I can build up a formula using my paste functions to just paste things together. And I'm just going to build up this formula in text, but I can pass that to LM. I can convert a text formula to a proper formula using this function as.formula. So my best model, I'm going to pass it in my formula to LM. My data is MP cars. And I can plot my predictions against my truth. And they fall pretty well on the 45-degree line. A more realistic example is with this TED Talks data set. So I'm going to load up this TED Talks data set, and I'll release this data as a slightly processed version of a data set. It has about 2,500 different TED Talks and 400 variables. The variables are like duration, film date, number of speakers, published date, views, which is what we're going to want to predict. And that has a bunch of stuff on word frequency, how many times children, creativity, culture, dance, education, how much they occur in the description of the TED Talk. So we might want to predict, if I want to make the optimal TED Talk, what key buzzwords should I include to get a bunch of views? So those are, again, some of the variables. Here's my views. So most things don't get watched a lot. Some of them get watched a ton. So it's a very kind of skewed distribution. If I look instead of at the log of my views, it looks much more normally distributed. And so it's probably going to be easier to predict because it's not going to have this kind of weird skewed behavior. So I'm going to subset down to just variables. All this line is doing is I'm just subsetting down to variables related to words. And I'm actually just going to subset to 100 different TED Talks. And so I'm just going to keep the views variable and then the word frequency data here. And I'm going to try and predict views from my word frequency data. And I've subset down to just 100 TED Talks, so my data set is 100 by 434. Now, if I try to just fit a model predicting views for my 100 TED Talks from these 434 variables, what's going to happen is I have more variables 434 than I do observations. And so you notice as I go through my beta hats here in my LM, I start to get these NAs, and actually I get a ton of these NAs showing up all over the place. So what's going on here? Well, basically I have if I want to estimate, I can look at the condition number. I can use this kappa function to look at the condition number of my data, or of my x transpose x. So if I grab the model matrix of x, it's 100 by 434, I can look at x transpose x, which is a 434 square matrix. But if I get my condition number, it's infinite. And why is it infinite? Because if I ask for the inverse using solve here, it says it's exactly singular. So singular matrix is not invertible and won't have a unique beta hat. And so R starts putting, basically has problems, starts you getting NAs in your beta hat. So what I can do is I can subset the variables. So I can use my reg subsets. I'm going to predict log views for my other stuff. I'm going to look at it, I have 100 different, I can include at most 100 different variables before I start running into invertibility issues. I'm going to use forward selection, and I'll fit these. And it's really, really, really fast, which is pretty impressive. And I could grab my, let's just call this AR2 for adjusted R squared. And I can plot these. I should plot these. Try this. And you notice I get this nice curve here. And it looks like somewhere in around 40, 50 variables maximizes my adjusted R squared. And so I think if I say which dot max adjusted R squared, it tells me it's 43 is the maximum. So I could build up my formula. This is some cute code to grab off those, to grab off that model with 43, 40, the kind of best. All I'm doing is I'm looking at my summary, that which matrix, grabbing the 43rd row, and pasting things together. So I get log views predicted from all these other variables here. I fit my best model, and then I could say plot my predictions against my truth. And it does pretty well. Let's add our 45-degree line here. Decent prediction. And I've done this in a case where, so I've selected down my variables to actually do a decent job at predicting. And so that's, real quick tour de force of how to select variables and solve some of these issues we've talked about in R.